Thorium is a naturally occurring nuclear fuel that is 4 times more common in the Earth's crust than uranium. It can be used in liquid fluoride thorium reactors to produce electrical energy, heat, and other valuable products. It's so energy dense that you can hold a lifetime supply of thorium energy in the palm of your hand. Right now we're burning fossil fuels because they're easy to find and because we can. Using fossil fuels entangles us in conflict in unstable regions of the world and costs money and lives. Things could be very different if we were using thorium. You see, in a lifter, we could use thorium about 200 times more efficiently than we're using uranium now. And because the lifter is capable of almost completely releasing the energy in thorium, this reduces the waste generated over uranium by factors of hundreds and by factors of millions over fossil fuels. One day I was in a friend's office at work and I noticed this book on the shelf, Fluid-Fueled Reactors, and I was interested and asked him if I could borrow it. Inside that book, I learned about research in the United States back in the 1950s into a kind of nuclear reactor that wasn't based on solid fuel or on water cooling. It didn't have the problems of the water-cooled reactor. And the reason why was pretty neat. It used a mixture of fluoride salts as a nuclear fuel, specifically the fluorides of lithium, beryllium, uranium, and thorium. Fluoride salts are remarkably chemically stable. They do not react with air and water. You have to heat them up to about 400 degrees Celsius to get them to melt. But that's actually perfect for trying to generate power in a nuclear reactor. Here's the real magic. They don't have to operate at high pressure. And that makes the biggest difference of all. This means that they don't have to be in heavy, thick steel pressure vessels. They don't have to use water for coolant, and there's nothing in the reactor that's going to make a big change in density like water. So the containment building around the reactor can be much smaller and close-fitting. Unlike the solid fuels that can melt down if you stop cooling them, these liquid fluoride fuels are already melted at a much, much lower temperature. Do we have enough thorium? Yes, we do. In fact, in the United States, we have over 3,200 metric tons of thorium that was stockpiled 50 years ago and is currently buried in a shallow trench in Nevada. This thorium, if used in lifters, could produce almost as much energy as the United States uses in 3 years. And thorium is not a rare substance either. There are many sites like this one in Idaho, where an area the size of a football field would produce enough thorium each year to power the entire world.